Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deep history of organized life on Earth, the civilizations that rose and fell long before human memory began. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, Earth spins in darkness. No sun penetrates the thick atmosphere of methane and ammonia that shrouds the planet like a burial cloth. No oceans reflect starlight back to space, for there are no oceans yet, only vast lakes of molten rock that stretch from horizon to horizon. The planet's surface glows with its own heat, a dull red ember cooling slowly under skies that rain droplets of vaporized stone. In this Hadean world, where temperatures soar beyond 1,000 degrees Celsius, the very concept of civilization seems not just impossible, but absurd, yet even here, in conditions that would instantly annihilate any form of life we know. The first experiments in organization begin. The Earth breathes in geological time, expanding and contracting as heat radiates into the void of space. Each breath takes millennia. Each exhale releases clouds of water vapor that rise high into the atmosphere, only to condense and fall again as scalding rain that never reaches the ground, boiling away in the superheated air long before impact. This is the planet's first weather system, crude and violent, but weather nonetheless the first hint that Earth might one day become a world where patterns emerge from chaos. Deep beneath the surface, in pockets of cooling rock, liquid water begins to gather. Not the water of rivers or seas, but superheated liquid trapped in crystal lattices, carrying dissolved minerals through underground chambers that stretch for thousands upon thousands of miles. These hidden networks pulse with chemical conversations more complex than anything happening on the barren surface above. Iron speaks to sulfur in the ancient language of electron exchange. Carbon whispers to phosphorus about the possibilities locked within their atomic structures. Silicon discusses architecture with oxygen, planning crystal palaces that will endure for eons. The Earth's magnetic field flickers and dies, reforms and collapses again, as the planet's core slowly differentiates into layers of increasing density. Lighter elements rise through the molten mantle like bubbles in a cosmic lava lamp, while heavier ones sink toward the center, following gravitational commands written in the fundamental laws of physics. This great sorting takes hundreds of millions of years to complete, a process so gradual that no single moment marks its beginning or end. Only the planet doesn't know it's sorting itself. It simply follows the quiet mathematics of density and heat, unaware that it's laying the foundation for every civilization that will follow. Scientists call this the Hadean Aeon, named for Hades, the underworld of Greek mythology where the dead wander in eternal twilight. The name seems appropriate for a world that appears lifeless, hostile to any form of organization or complexity. Yet even in this supposed hell, order emerges from chaos through nothing more dramatic than the patient rearrangement of atoms. Iron finds iron across vast distances, drawn together by electromagnetic forces too weak to notice but too persistent to resist. Silicon finds silicon, oxygen finds oxygen, creating the first stable structures in a world where nothing else seems permanent. These early mineral formations, the very first organized matter on Earth, begin to accumulate in patterns that follow mathematical rules no conscious mind has yet discovered. Crystals grow according to precise geometric principles, their lattices expanding atom by atom in perfect symmetry. Each crystal remembers the conditions of its formation, encoding information about temperature, pressure, and chemical composition in its molecular structure. They are Earth's first libraries, storing data about a world that no eye will witness for billions of years to come. The mystery lingers in every meteorite impact scar that still pocks the lunar surface. Every ancient zircon crystal that survives in modern rocks like a message from the deep past. How does a ball of cosmic debris, indistinguishable from countless other planetesimals drifting through space, begin to organize itself into something capable of supporting complexity? The answer hides in the slow accumulation of small differences, in the way cooling rock creates gradients of temperature and pressure that allow chemistry to become creative rather than merely destructive. Volcanic activity reaches levels that dwarf anything in recorded human history. Entire continents of lava emerge from the planetary interior, cool for a few million years, then melt again as fresh magma rises from below. The process repeats endlessly, each cycle adding new layers to the growing archaeological record of planetary evolution. What seems like endless destruction is actually construction on a timescale too vast for any individual consciousness to comprehend. The Earth builds itself through violence, each eruption adding to the eventual foundation upon which all future life will stand. The atmosphere thickens and thins in cycles measured in tens of millions of years. Water vapor condenses and evaporates in a dance between liquid and gas that will continue for eons. Sometimes, the planet's surface cools enough for the first tentative pools of liquid water to form, only to boil away again when volcanic activity resurges. These brief interludes of comparative calm are practice sessions for the stable oceans that will eventually cover most of the planet's surface. Even failure teaches the Earth about the delicate balance required for liquid water to persist. Impact craters appear and disappear as the planet's surface constantly renews itself through tectonic recycling. Each collision with asteroids and comets brings new materials from the outer reaches of the solar system, organic compounds, rare metals, and, most importantly, water locked in ice that sublimates instantly upon contact with the molten surface. These cosmic deliveries are adding up, molecule by molecule, contributing to chemical inventories that will prove essential for the emergence of life. The planet's rotation gradually slows as tidal forces from the newly formed moon begin their billion-year project of synchronization. Days that once lasted perhaps 6 hours stretch toward 12, then 18, creating longer periods of heating and cooling that allow more complex chemical reactions to unfold. The moon itself, born from a collision so massive it nearly shattered the early Earth, hangs in the sky as a constant reminder of the violent processes that created every stable feature of the world. Only took 400 million years for a molten planet to cool enough for liquid water to exist permanently on its surface. Only the first billion years of Earth's history to set the stage for every form of consciousness that would follow. Only the endless patience of geological time to transform chaos into the possibility of order. 1 degree of cooling at a time. The Hadean Earth prepares itself for inhabitants it cannot imagine, through processes it cannot understand, guided only by the inexorable mathematics of physics and chemistry, working on scales of space and time that reduce human civilization to a brief flicker in the cosmic dark. The oceans arrive not with fanfare, but with the patience of stone cooling under alien skies. For 300 million years, water vapor rises and condenses in endless cycles above a surface still too hot to hold liquid seas. Then one day, though day and night barely exist in the thick atmosphere, the temperature drops just low enough. Steam becomes rain, becomes the first permanent puddle. No larger than a lake, somewhere on the cooling crust of the early Earth. Within this puddle, chemistry begins to dream. The water tastes of iron and sulfur, bitter with dissolved minerals leached from volcanic rock. It carries no oxygen, that revolutionary gas has not yet been invented. Instead, hydrogen sulfide bubbles through the depths like the breath of sleeping dragons, while methane rises in lazy streams toward a surface that reflects no light back to space. This is not water as any living thing would recognize it, yet it cradles the possibility of everything that will follow. Deep beneath these first seas, where volcanic vents pierce the ocean floor, heat and chemistry conspire to create something unprecedented, the first organized communities on Earth. Here, in the crushing darkness of the deep ocean, bacteria unlike any that exist today begin to gather around these thermal chimneys. They feed not on light or organic matter, but on the chemical energy released when hot minerals mix with cold seawater. These chemosynthetic organisms represent Earth's first experiment in civilization, not individual cells struggling for survival, but communities working together to transform their environment. Scientists call them extremophiles, lovers of extreme conditions. Though the name misses something essential about their nature, they are not merely surviving in harsh conditions, they are creating the conditions that will make gentler forms of life possible. Each bacterial cell processes chemicals in ways that modify the water around it, creating microenvironments that other bacteria can exploit. Slowly, without planning or intention, they begin to engineer their world. The mystery deepens when we examine the fossil evidence they left behind. In rocks from this period, we find not random bacterial mats, but structured formations layered, organized deposits that suggest these early microorganisms were already cooperating in ways that produced architectural results. They built no pyramids or cathedrals, but they constructed something more fundamental, the chemical foundation for every ecosystem that would follow. Around these hydrothermal vents, the first biological cities begin to take shape. Layer upon layer of bacterial mats accumulate over millions of years, creating towering structures called stromatolites that can grow dozens of feet high. These are not random accumulations, but organized communities, with different species of bacteria occupying different niches within the growing towers. Some process sulfur compounds, others work with iron. Still others specialize in breaking down complex carbon molecules. Each group contributes to the maintenance of the whole, creating Earth's first example of biological urban planning. The chemistry of these early seas bears no resemblance to modern oceans. Iron dissolved in the water turns it rust red, while high concentrations of hydrogen sulfide create a rotten egg smell that would be toxic to most forms of life today. Yet for the bacteria that call these seas home, the chemistry is perfect. They have evolved in this environment, shaped by its constraints and opportunities. What seems hostile to us represents the height of habitability to them. These bacterial civilizations develop their own forms of communication, not language as we understand it, but chemical signals that coordinate behavior across vast distances. When one part of a bacterial mat detects changes in nutrient availability or temperature, it releases molecular messengers that alert neighboring communities. Information travels through the ocean in the form of dissolved chemicals, creating the first global communication network in Earth's history. Only the bacteria don't know they're communicating. They simply respond to chemical gradients in their environment, following ancient genetic programs that have been refined over millions of generations. Yet the result looks remarkably like intentional coordination. Bacterial mats pulse with synchronized activity. entire communities shifting their metabolism in response to signals from thousands of miles away. It's as if the ocean itself has developed a primitive form of consciousness, mediated by microorganisms too small to see without a microscope. The scale of these early civilizations defies imagination. Stromatolites eventually cover vast areas of the seafloor, creating underwater mountain ranges built entirely by living organisms. Some individual structures grow for millions of years, accumulating layer upon layer of bacterial communities in formations that dwarf any human city. The largest stromatolite complexes stretch for hundreds of miles and contain more individual organisms than have ever existed in human history. Yet for all their apparent success, these bacterial civilizations face a crisis they cannot anticipate, hidden within their own communities. A few rebellious bacteria begin experimenting with a dangerous new technology, photosynthesis. These early cyanobacteria learn to harvest energy directly from sunlight, freeing themselves from dependence on the chemical energy produced by hydrothermal vents. It seems like an obvious improvement, a step toward greater independence and efficiency. The rebels don't realize they're about to poison their world. Photosynthesis produces oxygen as a waste product, and oxygen is deadly to most forms of life that exist on early Earth. It's a highly reactive gas that breaks down the organic molecules essential for life, destroying cell membranes and disrupting the delicate chemistry that allows metabolism to function. For billions of bacteria, oxygen represents an extinction-level threat disguised as a byproduct of progress. But that catastrophe lies in the future. For now, in these early Archean seas, the first civilizations thrive in their iron-rich waters, building cities of stone and slime that will endure longer than the continents themselves. They work without rest, without awareness, transforming their planet one chemical reaction at a time. Only took them a few 100 million years to cover the seafloor with their constructions. Only the endless multiplication of microscopic architecture to begin reshaping the chemistry of an entire world. Only the patient accumulation of biological infrastructure to set the stage for the next great transformation in Earth's history. The ocean sleeps fitfully around these bacterial cities, heavy with dissolved metals and organic compounds, pregnant with possibilities that will not be realized for eons to come. In the deep water, where no light penetrates, the first civilizations of Earth continue their work of chemical engineering, unaware that they are laying the foundation for every form of complex life that will follow. The revolution begins quietly, as revolutions often do, with a few scattered rebels experimenting with dangerous new ideas. In shallow seas where sunlight penetrates the water column, certain bacteria begin to tinker with a process that will fundamentally alter the chemistry of their world. They call it nothing, for they have no language, but scientists will eventually name it photosynthesis, the art of capturing energy directly from starlight and storing it in molecular bonds. These early cyanobacteria appear unremarkable at first glance, hardly different from the countless other microorganisms that populate the ancient oceans. They form thin films on rocks and sediments, creating surfaces that shimmer with an oily blue-green iridescence. Yet within their microscopic bodies, they house molecular machinery more sophisticated than any technology humans have ever devised. Chlorophyll molecules arranged in precise arrays capture photons of light and convert them into chemical energy with an efficiency that modern solar panels cannot match. The process seems elegant, almost too perfect to have emerged through the random mutations and selective pressures that drive evolution. Light strikes the chlorophyll, exciting electrons to higher energy states. These energized electrons pass through a chain of protein complexes, each transfer releasing just enough energy to power the synthesis of energy-rich molecules. It's biochemical engineering of extraordinary sophistication, Yet it operates automatically, without conscious oversight or maintenance. But photosynthesis harbors a dark secret, a flaw that will prove catastrophic for most life on early Earth. The process requires water as a raw material, splitting H2O molecules to obtain the hydrogen atoms needed for building organic compounds. This leaves oxygen atoms as waste products, and the early cyanobacteria simply dump this toxic gas into their environment without consideration for the consequences. The mystery that puzzles scientists to this day involves the precise timing of photosynthesis's emergence. Chemical signatures in ancient rocks suggest that oxygen-producing cyanobacteria appeared quite suddenly in evolutionary terms, perhaps within a few tens of millions of years. This represents an astonishingly rapid development for such a complex biochemical process. How did random genetic changes produce such sophisticated molecular machinery so quickly? The fossil record offers few clues to this puzzle. At first, the oxygen released by photosynthesis poses little threat to the established order. The early atmosphere contains virtually no free oxygen, and the gas reacts immediately with iron dissolved in seawater, forming rusty precipitates that settle to the ocean floor. These banded iron formations create some of the most beautiful rock layers on Earth, alternating stripes of red iron oxide and black iron-rich minerals that record the planet's first experiments with oxygen chemistry. For millions of years, the oceans act as a vast chemical buffer, absorbing oxygen as quickly as the cyanobacteria can produce it. Iron continues to rust and precipitate, creating underwater snowfalls of metallic particles that drift down through the water column like red dust in a Martian sky. The process seems stable, sustainable. Even beneficial oxygen provides a new chemical pathway for energy storage, while iron precipitation helps clear the water of dissolved metals. Yet, the cyanobacteria multiply with relentless efficiency, spreading from shallow coastal waters into deeper ocean basins. Their populations double and redouble, each generation producing more oxygen than the last. They form vast floating mats that can be seen from space, if there were eyes in space to see them. These bacterial blooms represent the first large-scale terraforming project in Earth's history. Though the engineers remain unaware of the scope of their work, the bacterial communities develop increasingly sophisticated forms of organization as they spread across the globe. Different species specialize in different aspects of the photosynthetic process, with some focusing on light capture while others concentrate on carbon fixation. They arrange themselves in vertical layers within their mats, creating microenvironments where each species can operate at peak efficiency. It's division of labor on a microscopic scale, yet it produces results visible from orbit. Communication networks emerge within these cyanobacterial civilizations, mediated by chemical signals that coordinate behavior across enormous distances. When nutrients become scarce in one region, bacteria throughout the mat shift their metabolism to more efficient pathways. When light conditions change, entire communities alter their pigment production to optimize energy capture. The mats pulse with synchronized activity, their surfaces changing color in waves that sweep across hundreds of miles. The oxygen they produce begins to accumulate in the atmosphere as the iron in the oceans becomes fully oxidized. This marks a turning point in Earth's history, the moment when biological activity first begins to overwhelm geological processes in determining atmospheric composition. The sky, which has maintained roughly the same chemical composition for over 1 billion years, starts to change in ways that will make the planet unrecognizable to its original inhabitants. Only the cyanobacteria don't realize they're poisoning their world. They experience oxygen not as a waste product, but as a convenient way to dispose of unwanted atoms left over from photosynthesis. They have no concept of atmospheric chemistry or global climate, no understanding that their collective activities are engineering a planetary transformation that will take millions of years to complete. The first victims of the oxygen revolution are the bacteria that originally colonized the deep ocean vents. These anaerobic organisms, perfectly adapted to a world without free oxygen, begin to die as the toxic gas penetrates into their refuges. Their carefully constructed cities of living stone start to crumble as the chemical foundations of their metabolism are disrupted by the new atmospheric chemistry. Extinction sweeps through the bacterial world like a slow-motion plague, claiming species that have thrived for hundreds of millions of years. Yet even as the old order collapses, new forms of life begin to experiment with the dangerous chemistry of oxygen. Some bacteria learn to tolerate small amounts of the gas, then gradually evolve mechanisms to neutralize its toxic effects. A few pioneers even begin to harness oxygen's chemical reactivity, using it to extract energy from organic molecules with unprecedented efficiency. Only took 2 billion years for photosynthesis to completely transform Earth's atmosphere. Only the patient work of countless microscopic engineers to turn a reducing environment into an oxidizing one. Only the unintended consequences of biological innovation to set the stage for the next chapter in the planet's long experiment with organized complexity. The cyanobacteria continue their work, unaware that they are writing the chemical constitution for every form of complex life that will follow, including the organisms that will eventually evolve consciousness enough to understand what they accomplished. The dying begins slowly, almost imperceptibly, as oxygen levels rise from trace amounts to measurable concentrations in the ancient atmosphere. For the anaerobic bacteria that have dominated Earth for over 1 billion years, this represents the opening phase of the greatest mass extinction in planetary history. Yet they die without drama, without the spectacular collapse of ecosystems that will mark later extinction events. They simply fade away, one generation at a time, as their world becomes increasingly hostile to their ancient ways of life. In the deep ocean, where the oldest bacterial civilizations have built their cities of living stone, oxygen penetrates like a slow poison through water columns that have remained chemically stable for eons. The hydrothermal vent communities, those first experiments in organized complexity, find their carefully balanced chemical cycles disrupted by the new atmospheric chemistry. Bacteria that have processed sulfur compounds for hundreds of millions of years discover that oxygen interferes with their metabolic pathways, breaking down the very molecules they depend upon for survival. The stromatolites, those towering monuments to bacterial cooperation, begin to show signs of stress as oxygen levels continue to climb. The outer layers of these living structures start to die back, leaving behind only the hardiest species that can tolerate the increasingly toxic environment. What were once thriving communities of dozens of bacterial species become simplified ecosystems dominated by a few oxygen-resistant survivors. The great cities of the bacterial world begin their long decline into geological monuments. Scientists call this period the Great Oxygenation Event, though the name understates the magnitude of the transformation. This is not merely an atmospheric change, but a complete reorganization of life's relationship with chemistry itself. For nearly 2 billion years, life on Earth has been based on processes that avoid or exclude oxygen. Now, suddenly, this reactive gas becomes a dominant feature of the planetary environment, forcing every organism to adapt or perish. The mystery that haunts paleontologists involves the precise mechanism of this bacterial apocalypse. Oxygen is indeed toxic to anaerobic life, but the concentrations that develop during the Great Oxygenation Event are not immediately lethal. Instead, the gas seems to disrupt reproduction and growth in subtle ways that compound over many generations. Bacterial populations don't crash overnight. They slowly lose their ability to maintain their numbers. dwindling away over millions of years in a process too gradual for any individual organism to perceive. The chemistry of extinction operates on multiple levels simultaneously. Oxygen attacks the cell walls of anaerobic bacteria, making them more permeable and disrupting the careful regulation of internal chemistry that keeps metabolism functioning. It interferes with DNA replication, introducing errors that accumulate over generations until entire lineages lose the ability to reproduce successfully. Most insidiously, it reacts with the organic molecules that bacteria use to store energy, breaking down their food supplies from within. Yet even as the old bacterial world dies, new forms of life begin to explore the possibilities offered by an oxygen-rich environment. Some bacteria develop primitive antioxidant systems, molecular mechanisms that neutralize oxygen's destructive effects before they can damage essential cellular components. These early innovations are crude compared to the sophisticated biochemistry that will eventually evolve. But they represent the first steps toward a fundamentally different relationship with atmospheric chemistry. The survivors of the Great Oxygenation Event retreat to increasingly marginal environments where oxygen levels remain low. Deep sediments, underground water systems, and the interior regions of bacterial mats become refuges for anaerobic life. These bacterial communities persist to the present day, hidden in environments where oxygen cannot penetrate, living fossils of Earth's pre-oxygen world. They continue their ancient biochemistry in darkness, processing chemicals in ways that predate the atmospheric revolution by billions of years. The ocean chemistry transforms as dramatically as the atmospheric composition. Iron, which has colored the seas rust red for over 1 billion years, precipitates out as oxygen levels rise, leaving behind clear blue water that will become the signature color of Earth as seen from space. The banded iron formations that have been accumulating on the seafloor for eons cease to form, replaced by new types of sedimentary rocks that reflect the planet's changing chemistry. Methane, which has been a major component of the early atmosphere, begins to react with the increasing oxygen concentrations. The two gases combine to form water vapor and carbon dioxide in reactions that generate enough heat to influence global climate patterns. The greenhouse effect that has kept Earth warm despite the sun's lower luminosity begins to weaken as methane levels decline, threatening to plunge the planet into a global ice age. The bacterial communities that survive the initial wave of oxygenation face new challenges as their environment continues to evolve. Food webs that have remained stable for hundreds of millions of years collapse as key species disappear. Bacterial predators find their prey populations dwindling, while decomposer organisms struggle to process the chemical waste products of a changing ecosystem. The intricate networks of chemical communication that have connected bacterial communities across ocean basins begin to break down as the messenger molecules they depend upon are destroyed by oxygen. Some bacterial lineages attempt to adapt by forming partnerships with oxygen-tolerant species, creating the first crude examples of symbiotic relationships. These early alliances are unstable and often unsuccessful, but they represent experiments in cooperation that will eventually lead to some of the most important innovations in the history of life. The bacteria that learn to live together despite their chemical differences are the pioneers of a new kind of biological organization. The timescale of the Great Oxygenation Event stretches human comprehension to its limits. The transformation from an anaerobic to an aerobic world unfolds over hundreds of millions of years, a period longer than the entire fossil record of complex life. Individual bacterial generations live and die in matters of hours or days, yet the changes they collectively produce require geological ages to complete. It's evolution operating on a planetary scale, with consequences that will reverberate through every subsequent chapter of Earth's biological history. Only the dying bacteria don't understand what's happening to them. They experience oxygen not as a global environmental change, but as a local stress that makes life incrementally more difficult with each passing generation. They have no concept of atmospheric chemistry or mass extinction, no awareness that their individual struggles are part of a planetary transformation that will create the conditions for entirely new forms of complexity to emerge. Only took 500 million years for oxygen to reshape the fundamental chemistry of life on Earth. Only the patient accumulation of toxic waste products to trigger the most comprehensive reorganization of biological systems in planetary history. Only the unintended consequences of photosynthetic innovation to clear the stage for new forms of life that could harness the destructive power of oxygen and transform it into the foundation for unprecedented biological complexity. The ancient world dies quietly, one bacterial community at a time, making room for possibilities it could never have imagined. In the aftermath of the Great Dying, in waters now clear and blue where iron once painted the seas rust red, something unprecedented begins to happen. Small cells, perhaps no larger than modern bacteria, start to approach each other with what can only be described as diplomatic intent. They do not consume each other, as predatory bacteria have done for eons. Instead, they negotiate. They explore the possibility of coexistence, of mutual benefit, of becoming something greater than the sum of their individual parts. These early experiments in cellular diplomacy unfold over millions of years, each interaction a tentative exploration of biological partnership. The larger cells possess sophisticated internal machinery for processing nutrients and managing cellular waste, but they lack the ability to efficiently harness the energy contained in oxygen molecules. The smaller cells, descendants of the cyanobacteria that triggered the atmospheric revolution, have mastered the art of oxygen metabolism but struggle to compete for resources in the post-extinction world. The negotiations begin accidentally, when larger cells attempt to consume smaller ones as food. But something goes wrong, or perhaps, from the perspective of evolutionary innovation, something goes spectacularly right. Instead of digesting their intended prey, some large cells discover that the smaller organisms continue to function within their cellular boundaries. The would-be predators become inadvertent hosts, while their intended meals transform into permanent residents. Scientists call this process endosymbiosis, the establishment of one organism inside another for mutual benefit. The name makes the process sound orderly, planned, civilized. In reality, these early partnerships are chaotic affairs, fraught with biological miscommunication and evolutionary false starts. Most attempts at cellular cohabitation end in failure, with one partner overwhelming the other, or both dying from the stress of enforced intimacy. The mystery that confounds researchers involves the mechanism by which these partnerships become permanent and hereditary. How do two independent organisms, each with its own genetic agenda and evolutionary history, learn to coordinate their reproduction so precisely that they function as a single biological entity? The molecular details of this transition remain largely hidden in rocks too old to preserve the delicate structures where such negotiations would have taken place. Yet occasionally, the diplomacy succeeds. A large cell learns to provide nutrients and protection to its smaller residents while receiving energy in return. The smaller cells sacrifice their independence but gain security and access to resources they could never obtain on their own. Over many generations, the partnership deepens until neither participant can survive without the other. What began as a temporary arrangement becomes a permanent merger, a new kind of organism that possesses capabilities neither parent species could achieve alone. These early eukaryotic cells, organisms with complex internal structures, represent Earth's first successful experiments in biological federalism. They are not single entities, but cooperative unions. Cellular governments where different organelles specialize in different functions while contributing to the welfare of the whole. The nucleus manages genetic information and coordinates reproduction. Mitochondria handle energy production and cellular respiration. Each component maintains its own identity while participating in the larger project of keeping the composite organism alive. The negotiations that establish these partnerships require sophisticated chemical communication systems. Cells must learn to recognize compatible partners while avoiding potentially harmful associations. They develop molecular signals that identify friend from foe, self from other, cooperator from exploiter. These chemical languages are more complex than any communication system that has previously existed on Earth, allowing cells to coordinate their behavior with precision that borders on the telepathic. Some partnerships fail catastrophically, with one partner overwhelming the other in biological coups that destroy both participants. Other alliances succeed too well, producing organisms so efficient at exploiting their environment that they exhaust their resources and collapse from their own success. The sustainable partnerships are those that find the delicate balance between cooperation and independence, allowing each participant to maintain its essential character while contributing to the collective enterprise. The successful eukaryotic cells begin to experiment with cellular democracy, developing internal governance systems that coordinate the activities of their various organelles. Decision-making processes emerge that allow different parts of the cell to communicate their needs and coordinate their responses to environmental challenges. These primitive cellular governments operate without consciousness or intention, yet they display organizational sophistication that rivals human political institutions. The energy budgets of these composite cells dwarf anything that has previously existed in the biological world. Mitochondria can extract nearly 20 times more energy from nutrients than anaerobic bacteria, providing their host cells with unprecedented metabolic resources. This energy abundance allows eukaryotic cells to grow much larger than their bacterial predecessors and to invest in complex internal structures that would be prohibitively expensive for simpler organisms to maintain. With their superior energy resources, eukaryotic cells begin to experiment with new forms of biological architecture. They develop internal scaffolding systems that allow them to maintain complex shapes and resist deformation. They create specialized compartments for different cellular functions, establishing internal economies where materials and energy flow between organelles like trade goods between allied nations. The interior of a eukaryotic cell becomes a bustling metropolis of molecular activity. These cells also pioneer new approaches to genetic inheritance, developing systems that allow them to pass on not just their own genetic material, but also the genetic information of their symbiotic partners. The mechanics of this coordinated reproduction require exquisite timing and chemical coordination between organisms that evolved independently for billions of years. Yet somehow, through trial and error spread across millions of generations, they develop reproductive protocols that ensure the stable transmission of their composite genetic heritage. The larger size and greater complexity of eukaryotic cells make them vulnerable to new forms of predation and environmental stress. They develop increasingly sophisticated defense mechanisms, including the ability to rapidly alter their internal chemistry in response to threats. Some eukaryotic cells learn to form protective coverings, while others develop the ability to move away from dangerous conditions. The arms race between predator and prey intensifies as both sides gain access to the metabolic resources provided by endosymbiotic partnerships. Only the cells don't understand that they're creating the foundation for every complex organism that will ever exist on Earth. They experience their partnerships not as evolutionary breakthroughs, but as daily negotiations over resources and reproductive scheduling. They have no awareness that their diplomatic experiments are establishing the cellular architecture that will eventually support consciousness complex enough to study their own evolutionary origins. Only took several 100 million years for simple predation to evolve into permanent partnership. Only the endless repetition of cellular diplomacy to establish the biological basis for all complex life. Only the patient work of molecular negotiation to create organisms capable of supporting the energy demands of multicellular bodies, nervous systems, and eventually, the metabolic requirements of contemplative minds that can appreciate the elegant solutions their ancestors discovered through blind experiment in the ancient seas. The parliament of organelles convenes within each eukaryotic cell, conducting its business in the chemical languages that have evolved over hundreds of millions of years of cohabitation. There are no formal proceedings, no scheduled meetings, no recorded minutes of their deliberations. Yet the governance that emerges from these molecular assemblies rivals any political system devised by conscious minds. Each organelle maintains its autonomy while contributing to the collective welfare, creating cellular democracies that function with remarkable stability across geological time. Mitochondria, those former bacteria that have become the powerhouses of eukaryotic cells, maintain their own genetic constitutions alongside the nuclear genome. They reproduce according to their own schedules, dividing when cellular energy demands require additional capacity rather than waiting for the host cell to undergo reproduction. This semi-independence creates ongoing tensions within the cellular confederation, as mitochondria pursue their own evolutionary interests while remaining dependent on nuclear genetic instructions for essential cellular functions. The nucleus assumes the role of central government, housing the vast majority of genetic information and coordinating the expression of genes that regulate cellular behavior. Yet its authority is not absolute. Mitochondria retain enough genetic independence to occasionally rebel against nuclear control, producing variant protein forms that can alter cellular metabolism in ways that benefit mitochondrial reproduction at the expense of cellular efficiency. These molecular conflicts play out over thousands of generations, creating evolutionary pressures that shape both partners, chloroplasts, where they exist, add another voice to the cellular parliament. These descendants of cyanobacteria bring their own genetic heritage and metabolic expertise to the Confederation, specializing in the capture and conversion of solar energy. They negotiate constantly with mitochondria over energy distribution, sometimes competing for cellular resources, sometimes cooperating to optimize overall energy production. The resulting biochemical networks are more complex than any ecosystem that has previously existed on Earth. The mystery that puzzles biologists involves the remarkable stability of these ancient partnerships. Endosymbiotic relationships are notoriously fragile in modern organisms, often breaking down when environmental conditions change or when one partner evolves in ways that disadvantage the other. Yet the mitochondrial and chloroplast alliances have persisted for over 1 billion years, surviving ice ages, asteroid impacts, and massive atmospheric changes that have destroyed countless other forms of life. Communication between organelles relies on sophisticated molecular messaging systems that operate continuously within each cell. Mitochondria monitor cellular energy levels and adjust their output accordingly, while sending chemical signals that inform the nucleus about metabolic conditions. The nucleus responds by altering gene expression patterns, producing proteins that optimize cellular function for current conditions. Chloroplasts contribute their own signals about light availability and carbon dioxide concentrations, creating information networks that rival modern telecommunications in their complexity. These cellular governments develop increasingly sophisticated systems for managing internal trade. Nutrients flow between organelles along carefully regulated pathways with molecular checkpoints that ensure fair distribution of resources. Waste products are processed through multi-step recycling systems that minimize cellular pollution while maximizing resource efficiency. The interior of a eukaryotic cell becomes a model of sustainable industrial organization, achieving levels of efficiency that human societies can only aspire to match. The organelles establish collective defense mechanisms that protect the cellular confederation from external threats. When toxic substances enter the cell, different organelles coordinate their responses to neutralize the danger. Mitochondria alter their metabolism to process harmful chemicals, while the nucleus activates genes that produce defensive proteins. Chloroplasts adjust their photosynthetic activity to minimize damage from environmental stresses. These coordinated responses require precise timing and chemical communication between organelles that evolved independently for billions of years. Reproductive negotiations between organelles represent some of the most complex biological processes ever to evolve. When a eukaryotic cell prepares to divide, each organelle must coordinate its own reproduction to ensure that both daughter cells receive adequate numbers of all essential components. Mitochondria must balance their own reproductive interests with the needs of the host cell, while chloroplasts must time their division to coincide with cellular reproduction. The molecular mechanisms that coordinate these processes involve hundreds of proteins and regulatory molecules working in precise sequence. The energy economics of eukaryotic cells allow them to invest in biological luxuries that simpler organisms cannot afford. They develop elaborate internal transport systems that move materials between organelles with remarkable efficiency. They construct complex protein machines that can repair damaged cellular components and recycle worn-out molecular machinery. They maintain sophisticated quality control systems that monitor cellular function and eliminate defective proteins before they can cause problems. Some eukaryotic cells begin experimenting with sexual reproduction, developing mechanisms that allow two cells to merge temporarily and exchange genetic material before separating again. This innovation requires unprecedented levels of coordination between multiple cellular governments, as organelles from two different lineages must somehow negotiate the terms of genetic exchange without destroying the carefully balanced partnerships that allow eukaryotic life to function. The success of eukaryotic cells creates new ecological opportunities and challenges. Their larger size and greater metabolic capacity allow them to exploit resources that remain inaccessible to bacterial communities. They begin to diversify into forms specialized for different environmental niches, developing distinctive cellular architectures optimized for specific conditions. Some become expert hunters, developing sophisticated mechanisms for capturing and digesting other cells. Others specialize in photosynthesis, creating cellular factories that convert sunlight into chemical energy with unprecedented efficiency. The arms race between eukaryotic predators and prey drives rapid evolutionary innovation as both sides develop increasingly sophisticated attack and defense mechanisms. Prey species evolve protective shells, toxic secretions, and rapid escape responses. Predators counter with more effective digestive enzymes, improved sensory systems, and specialized appendages for capturing elusive targets. The biological technology race accelerates beyond anything seen in the previous 3 billion years of Earth's history. Yet the most significant experiments involve cooperation rather than competition. Some eukaryotic cells begin forming temporary aggregations, coming together in response to environmental stresses or resource opportunities before dispersing again when conditions change. These primitive multicellular assemblies represent the first tentative steps toward the complex organisms that will eventually dominate terrestrial ecosystems. Only the organelles don't understand that they're pioneering the governmental systems that will eventually support complex multicellular life. They experience their partnerships not as political experiments, but as biochemical necessities, daily negotiations over resources and reproductive scheduling that happen to create stable cellular confederations. They have no awareness that their diplomatic innovations are establishing the organizational principles that will eventually govern tissues, organs, and entire organisms. Only took a few 100 million years for endosymbiotic partnerships to evolve into stable cellular governments. Only the patient refinement of molecular communication systems to create the biological basis for complex life. Only the endless negotiation between ancient lineages to establish the cooperative frameworks that will eventually support nervous systems complex enough to contemplate their own evolutionary origins and governance structures, sophisticated enough to recognize the elegant political solutions their cellular ancestors discovered through blind experiment in the patient waters of deep time. The blueprints for something unprecedented begin to emerge in the quiet margins of ancient seas, written not in DNA alone, but in the spaces between cells where chemistry becomes architecture. Individual eukaryotic cells, those successful federations of organelles, start to linger near each other after reproduction instead of immediately dispersing to seek their separate fortunes. They cluster in groups of 2, then 4, then dozens, held together by molecular adhesives that represent the first experiments in biological mortar. These early aggregations are temporary affairs, lasting perhaps days or weeks before environmental pressures force the constituent cells to separate and resume their solitary existence. Yet during these brief interludes of cooperation, something remarkable happens. The cells begin to specialize, with some members of the group focusing on nutrient capture, while others concentrate on waste processing or predator detection. It's the first hint that individual cells might surrender their autonomy in exchange for the security and efficiency of collective action. The transition from independence to interdependence unfolds with glacial patience across millions of years. Cells that have been complete organisms in their own right gradually accept limitations on their individual capabilities in exchange for enhanced collective survival. Some cells sacrifice their ability to reproduce, becoming sterile workers that contribute to group welfare without passing on their own genetic lineage. Others abandon their capacity for independent feeding, relying entirely on nutrients provided by their specialized neighbors. Scientists struggle to identify the precise moment when these cellular confederations cross the threshold from temporary association to permanent organism. The fossil record preserves only the hard parts of ancient life, offering few clues about the soft tissues and biochemical negotiations that drive the transition to multicellularity. What remains are tantalizing traces of organized structures in rocks nearly 1 billion years old, evidence that cells were already experimenting with architectural cooperation long before any complex organisms appear in the fossil record. The mystery deepens when researchers examine the genetic mechanisms that coordinate multicellular development. The molecular tools required for cellular specialization and communication are extraordinarily complex, involving thousands of genes that must work in precise coordination. How did such sophisticated systems evolve from the relatively simple genetic programs that govern single-celled life? The evolutionary pathways that led from cellular independence to multicellular cooperation remain largely hidden in the deep past. Communication between cells within these early multicellular organisms requires the development of entirely new molecular languages. Cells must learn to send and receive chemical signals that coordinate their behavior with neighbors they can't even see. They develop molecular messengers that carry information about nutrient availability, environmental threats, and reproductive status. These cellular communication networks become increasingly sophisticated as multicellular organisms grow in size and complexity. The first multicellular organisms resemble living quilts, flat sheets of cells that cover rocks and sediments in shallow marine environments. Each cell retains much of its individual identity while contributing to the collective structure. The organisms can repair damage by having neighboring cells divide to fill gaps left by dead or injured members. They can grow indefinitely by adding new cells to their margins. They represent a new kind of biological entity, neither fully individual nor truly collective. Some cellular communities begin experimenting with three-dimensional architecture, creating multicellular structures that rise above the seafloor like primitive skyscrapers. These early towers are built through the coordinated division and adhesion of thousands of cells, each one following genetic instructions that tell it when to divide, where to attach, and what specialized function to perform. The resulting organisms achieve sizes and structural complexity impossible for any single cell to attain. The energy requirements of multicellular life force innovations in cellular logistics that rival the supply chains of modern industrial societies. Nutrients must be distributed from specialized feeding cells to interior regions where cells have no direct access to the environment. Waste products must be collected from throughout the organism and expelled through designated disposal systems. Oxygen must be transported from surface cells that can exchange gases with seawater to deeper cells that would otherwise suffocate. These early multicellular organisms developed the first biological transport systems, creating networks of channels and vessels that move materials throughout their bodies. Some species evolve pumping mechanisms that actively circulate fluids, while others rely on passive diffusion and cellular contractility. The most successful designs balance the energy costs of maintaining transport systems against the benefits of improved resource distribution. Predation pressure drives rapid innovation in multicellular defense strategies. Some organisms develop protective outer layers of specialized cells that form biological armor against cellular predators. Others evolve the ability to contract rapidly, pulling vulnerable feeding surfaces away from danger. A few species experiment with chemical warfare, producing toxic compounds that deter attackers while avoiding self-poisoning. The reproductive strategies of multicellular organisms create new biological challenges that have no precedent in the single-celled world. How does an organism composed of thousands of cells coordinate the production of reproductive cells that can survive independently? Some early multicellular species solve this problem by fragmenting during reproduction, with each fragment growing into a complete organism. Others develop specialized reproductive cells that carry the genetic information needed to rebuild the entire multicellular structure from a single starting point. Sexual reproduction becomes increasingly complex as multicellular organisms evolve mechanisms for combining genetic material from two different individuals. This requires the development of chemical recognition systems that allow organisms to identify compatible mates while avoiding sterile or harmful combinations. The molecular machinery needed for sexual reproduction involves some of the most sophisticated biochemical processes ever to evolve. The success of multicellular life creates new ecological opportunities as organisms begin to exploit three-dimensional space above the sea floor. Tall multicellular structures can capture nutrients and light that remain inaccessible to their single-celled competitors. They create new habitats for smaller organisms, establishing the first complex ecosystems where multiple species interact in intricate food webs. Yet multicellularity also creates new vulnerabilities that don't exist for single-celled organisms. Damage to key structural elements can compromise entire regions of a multicellular body. Communication failures between cells can lead to uncontrolled growth or inappropriate specialization. The coordination required for multicellular life introduces countless opportunities for things to go wrong. The early multicellular organisms experiment with different organizational strategies, testing the boundaries between cooperation and competition within their own bodies. Some species maintain strict cellular hierarchies where specialized coordinator cells direct the activities of worker cells. Others develop more egalitarian systems where decisions emerge from collective cellular behavior without centralized control. Only the cells don't understand that they're writing the first chapters in the long history of complex life on Earth. They experience multicellularity not as an evolutionary breakthrough, but as a series of biochemical negotiations over adhesion molecules and nutrient distribution. They have no awareness that their experiments in cellular cooperation are establishing the architectural principles that will eventually support bodies complex enough to house consciousness and nervous systems sophisticated enough to study their own multicellular origins. Only took several 100 million years for cellular independence to evolve into multicellular cooperation. Only the patient negotiation of adhesion and specialization to create the biological foundation for complex organisms. Only the endless experimentation with cellular architecture to establish the organizational frameworks that will eventually support tissues, organs, and organ systems sophisticated enough to generate the thoughts contemplating their own evolutionary origins in the quiet laboratories of deep time. In the soft sediments of Ediacaran sea floors, 600 million years ago. Earth's first large-scale multicellular communities begin to establish their strange parliaments of flesh. These organisms bear no resemblance to anything alive today. They are quilted creatures, frond-like beings, disc-shaped entities that look more like abstract sculptures than living things. Yet, within their alien geometries, they pioneer the first experiments in complex biological governance, creating societies of cells that coordinate their activities across bodies measured in feet rather than microscopic units. The Ediacaran organisms inhabit a world still foreign to modern sensibilities. The oceans contain no predators with shells or teeth, no creatures that hunt by pursuit or ambush. Instead, these early multicellular societies feed by filtering nutrients from seawater or absorbing dissolved organic compounds through their extensive surface membranes. They live in a garden world where competition involves patient resource gathering rather than violent conquest, where survival depends on efficiency rather than aggression. Dickinsonia, one of the most enigmatic Ediacaran organisms, grows to over 3 feet in length while maintaining a body plan of elegant simplicity. Its segmented form consists of repeated units that expand in coordinated waves as the organism matures, each segment following genetic instructions that somehow coordinate growth across the entire body. The creature moves across the sea floor with glacial patience, leaving behind distinctive fossil tracks that record its methodical progress through bacterial mats. The mystery that confounds paleontologists involves the fundamental biology of these ancient organisms. They possess no obvious mouths, digestive systems, or reproductive organs. Their bodies show no evidence of the complex organ systems that characterize all later multicellular life. Yet they achieve remarkable size and structural complexity through biological mechanisms that remain largely incomprehensible. How did they feed, reproduce, and coordinate the activities of millions of cells without the anatomical infrastructure that later organisms require for such functions? Kimberella represents another experiment in Ediacaran biological architecture, combining elements that suggest both animal and plant characteristics. Its asymmetrical body plan includes what appears to be a muscular foot for locomotion and feeding structures that may have been used to scrape bacterial films from rock surfaces. The organism demonstrates that even in this early period of multicellular evolution, life was already experimenting with complex behavioral strategies that required coordination between different body regions. These organisms developed the first chemical communication networks that operate across macroscopic distances. Cells in one part of an Ediacaran body can send molecular signals that coordinate the behavior of cells many inches away, creating unified responses to environmental changes. When nutrients become scarce in one region, the entire organism can shift its metabolic strategy or alter its growth patterns. These primitive nervous systems operate without neurons or synapses, relying instead on diffusion-based chemical networks that work slowly but effectively. The Ediacaran communities establish complex ecological relationships that foreshadow the intricate food webs of later periods. Some species appear to be specialized filter feeders that extract nutrients from water flowing past their elaborate body surfaces. Others develop symbiotic relationships with bacterial communities, providing protected environments for microorganisms in exchange for metabolic services. A few species may have been early predators, though their hunting strategies would have been completely unlike anything seen in later evolutionary periods. Fractal geometries appear repeatedly in Ediacaran body plans, with organisms like Charnia developing branching patterns that maximize surface area while minimizing structural complexity. These mathematical solutions to biological engineering problems represent some of the most elegant designs ever produced by evolutionary processes. The organisms achieve remarkable efficiency in nutrient capture and gas exchange through body plans that follow precise geometric rules discovered through millions of years of trial and error. The reproductive strategies of Ediacaran organisms remain one of the greatest puzzles in paleobiology. Many species show no evidence of sexual organs or obvious mechanisms for genetic exchange. Some appear to reproduce through fragmentation, with pieces of the parent organism growing into complete individuals. Others may have used spore-like propagules or employed reproductive strategies so different from later organisms that they leave no recognizable fossil traces. Environmental engineering becomes a hallmark of Ediacaran ecosystems as organisms begin to modify their surroundings in ways that benefit their communities. Some species create sediment-stabilizing mats that prevent erosion and provide stable substrates for other organisms. Others develop chemical techniques for altering local pH or oxygen concentrations, creating microenvironments that support specialized biological communities. The body plans of Ediacaran organisms often incorporate modular designs that allow for flexible responses to environmental challenges. Organisms like Sprigina can add or remove body segments based on resource availability, growing larger when conditions are favorable and contracting when nutrients become scarce. This architectural flexibility represents an early solution to the problem of surviving in variable environments. Though it requires sophisticated cellular communication systems to coordinate growth and regression across the entire body, some Ediacaran communities develop primitive forms of collective behavior, with multiple organisms coordinating their activities across large areas of seafloor. These early experiments in multicellular cooperation foreshadow the complex social behaviors that will later evolve in more advanced organisms. Groups of organisms may synchronize their feeding activities, reproductive cycles, or responses to environmental threats, creating biological networks that span entire ecosystems. The chemical ecology of Ediacaran environments supports forms of biological interaction that have no modern parallels. Organisms communicate through dissolved compounds that travel through seawater, creating chemical landscapes where information flows freely between different species. These early experiments in biochemical communication establish the foundation for the more sophisticated chemical signaling systems that will later enable complex behaviors in advanced organisms. The decline of Ediacaran faunas marks the end of Earth's first experiment with large-scale multicellular life. These organisms disappear from the fossil record with mysterious suddenness, leaving behind only their distinctive impressions in ancient sediments. Their extinction may have been caused by changing ocean chemistry, the evolution of new predatory strategies, or competition from organisms with more efficient body plans. Whatever the cause, their disappearance clears the evolutionary stage for the dramatic diversification of life that will characterize the following Cambrian period. Yet the Ediacaran organisms leave behind more than fossil impressions. Their experiments in multicellular organization establish many of the fundamental principles that will guide the evolution of all later complex life. They demonstrate that large, coordinated biological systems can emerge from communities of cooperating cells, that organisms can achieve remarkable complexity through simple repeated patterns, and that life can engineer its environment in ways that benefit entire ecological communities. Only the Ediacaran organisms don't understand that they're conducting Earth's first experiments in complex biological governance. They experience their multicellular coordination not as political innovation, but as biochemical necessity. Cellular negotiations that happen to produce organisms capable of modifying their environment on geological scales. They have no awareness that their organizational experiments are establishing the biological foundations for nervous systems, circulatory systems, and digestive systems that will eventually support consciousness complex enough to study their own evolutionary heritage. Only took a few tens of millions of years for simple multicellular aggregations to evolve into complex Ediacaran communities. Only the patient refinement of cellular cooperation to create Earth's first large-scale biological societies, only the endless experimentation with multicellular architecture to establish the organizational principles that will eventually support the anatomical complexity of thinking organisms, capable of contemplating their own origins in the fossil impressions left by these strange pioneers in the ancient sediments of deep time. The piece ends with startling suddenness. In the space of perhaps 20 million years, a geological instant, the gentle Ediacaran world gives way to something unprecedented in Earth's history, an arms race. The Cambrian explosion begins not with a bang, but with the patient evolution of hard parts, as organisms discover that calcium carbonate and chitin can be molded into shields, swords, and sophisticated optical instruments. The age of biological warfare has begun. The first shells appear in the fossil record like scattered pieces of alien armor, simple cones and tubes that protect their soft-bodied inhabitants from newly evolved threats. These early experiments in biological engineering are crude by later standards, little more than mineral umbrellas that organisms can retreat beneath when danger approaches. Yet they represent a fundamental shift in the evolutionary arms race, the moment when defense becomes as important as efficiency in determining biological success. Trilobites emerge as the master engineers of this new world, developing compound eyes with hundreds of individual lenses that can detect movement across the seafloor with remarkable precision. Each eye contains calcite crystals arranged in perfect geometric arrays, creating optical systems that function according to the same physical principles that govern modern telescopes and microscopes. These are not accidental arrangements, but precise biological technologies that require sophisticated genetic programs to construct and maintain. The mystery that puzzles evolutionary biologists involves the extraordinary rapidity of Cambrian innovation. Complex anatomical structures that should require millions of years to evolve appear in the fossil record within relatively brief time intervals. Eyes, shells, jointed appendages, and sophisticated nervous systems all emerge during the same geological period, suggesting that evolutionary processes were operating under conditions very different from those that prevail today. Anomalocaris, the apex predator of Cambrian seas, grows to over 6 feet in length and develops flexible grasping arms lined with sharp spines for capturing prey. Its compound eyes are the largest known from any period of Earth's history, suggesting that vision becomes critically important in this new world of predators and prey. The creature represents the first large-scale biological experiment with active hunting, establishing behavioral patterns that will persist throughout the subsequent history of complex life. The evolutionary pressure to avoid being eaten drives rapid innovation in defensive strategies as organisms experiment with spines, shells, burrowing behaviors, and chemical deterrents. Some species develop the ability to shed body parts when attacked, regrowing lost appendages over subsequent molting cycles. Others evolve sophisticated camouflage systems that allow them to blend seamlessly with their surroundings. The most successful designs balance the metabolic costs of defense against the survival benefits of avoiding predation. Burgess Shale organisms represent some of the most bizarre experiments in biological design ever preserved in the fossil record. Wiwaxia combines elements of mollusks and annelid worms in a body plan that has no modern equivalent. Opabinia develops a flexible proboscis tipped with a grasping claw, creating a feeding mechanism unlike anything that evolved before or since. These evolutionary experiments demonstrate that the early Cambrian was a period of extraordinary biological creativity, when natural selection tested anatomical possibilities that were later abandoned or refined. The development of complex nervous systems accelerates during the Cambrian, as organisms face increasingly sophisticated challenges in predator detection, prey capture, and environmental navigation. Simple networks of nerve cells evolve into centralized processing systems that can integrate information from multiple sensory modalities and coordinate rapid behavioral responses. These primitive brains are tiny compared to later developments, but they represent the first biological computers capable of real-time decision-making. Arthropods pioneer the development of jointed appendages that can be modified for a remarkable variety of functions. The same basic limb architecture serves for walking, swimming, feeding, fighting, and reproduction through subtle changes in segment proportions and joint mechanics. This modular approach to anatomical design allows rapid evolutionary experimentation with new ecological strategies while maintaining basic structural integrity. The chemistry of shell and skeleton construction requires organisms to solve complex biomineralization problems that have no precedent in earlier evolutionary periods. Cells must learn to control the nucleation and growth of mineral crystals with remarkable precision, creating structures that combine the hardness of rock with the flexibility needed for growth and repair. The molecular mechanisms that govern biomineralization involve hundreds of specialized proteins working in carefully coordinated sequences. Predator-prey relationships drive the evolution of increasingly sophisticated behavioral strategies as both hunters and hunted develop new tactics for success. Some predators evolve ambush strategies that rely on concealment and rapid attack. Others develop pursuit capabilities that allow them to chase down fleeing prey across open seafloor. Prey species counter with enhanced sensory systems, faster escape responses, and group defensive behaviors that reduce individual risk. The ecological complexity of Cambrian ecosystems exceeds anything that has previously existed on Earth. Multiple trophic levels develop as organisms specialize for different roles in increasingly intricate food webs. Primary producers, herbivores, predators, scavengers, and decomposers establish ecological relationships that create stable ecosystem dynamics capable of supporting remarkable biological diversity. Burrowing becomes a major evolutionary innovation as organisms discover that sediments provide protection from surface predators, while offering access to nutrients buried in the seafloor. The development of efficient digging appendages and muscular systems for underground locomotion requires significant anatomical modifications, but the benefits include access to unexploited ecological niches and refuge from the intensifying predation pressure of surface environments. Some Cambrian organisms begin experimenting with colonial organization, creating biological confederations where multiple individuals cooperate for mutual benefit. These early experiments in social behavior foreshadow the complex societies that will later evolve in insects, vertebrates, and other lineages. The coordination mechanisms required for successful colonial life involve sophisticated communication systems and division of labor between different colony members. The preservation of soft tissues in exceptional fossil deposits provides unprecedented insights into the anatomy and behavior of Cambrian organisms. Muscle fibers, nervous systems, digestive tracts, and even cellular structures can be observed in specimens that capture biological details usually lost during fossilization. These remarkable preservation events offer windows into the daily lives of organisms that lived over 500 million years ago. The global distribution of Cambrian faunas suggests that many innovations evolved independently in different parts of the world's oceans, indicating that the evolutionary pressures driving biological complexity were operating on a planetary scale. Similar anatomical solutions to ecological challenges appear in geographically isolated regions, demonstrating that the fundamental problems of multicellular life have limited numbers of viable solutions. Only the Cambrian organisms don't understand that they're conducting the greatest experiment in biological innovation in Earth's history. They experience their anatomical arms race not as evolutionary progress, but as immediate survival challenges, daily struggles with predators and prey that happen to drive the development of complex sensory systems, sophisticated behaviors, and anatomical structures that will define the basic architecture of animal life for the next 500 million years. Only took 20 million years for simple multicellular organisms to evolve into complex animals with eyes, brains, and sophisticated behavioral capabilities. Only the relentless pressure of predation and competition to drive the rapid evolution of anatomical innovations that establish the biological foundations for every complex ecosystem that will follow. Only the endless experimentation with biological technology to create organisms sophisticated enough to house nervous systems capable of experiencing consciousness and eventually developing the intellectual capacity to study their own evolutionary origins in the fossil treasures of ancient seas. In the warm, shallow seas that spread across much of the Cambrian world, a new form of civilization begins to take shape beneath the waves. Not built by conscious architects, but by countless tiny polyps, each no larger than a fingernail, working together to construct underwater cities that will dwarf any human settlement in both scale and permanence. The first great reef-building corals begin their patient work of transforming dissolved minerals into limestone architecture, creating biological metropolises that will persist for hundreds of millions of years. Each coral polyp represents a marvel of biological engineering, a simple animal that has learned to farm algae within its own tissues while simultaneously extracting calcium carbonate from seawater to build its skeletal home. The symbiotic algae provide their coral hosts with sugars produced through photosynthesis, while the corals offer their microscopic partners protection and access to nutrients. This ancient partnership between animal and plant establishes one of the most successful collaborative ventures in the history of life. The construction process unfolds with architectural precision that rivals any human engineering project. Each polyp secretes a cup-shaped skeleton that serves as both home and foundation for future growth. As polyps reproduce through budding, they create interconnected networks of limestone chambers, each new generation building upon the skeletal remains of their ancestors. Over time, these accumulating structures grow into massive limestone reefs that can be seen from space. Scientists studying modern reef systems estimate that some coral colonies may live for thousands of years, making them among the oldest multicellular organisms on Earth. The largest coral structures, like Australia's Great Barrier Reef, contain limestone deposits that have been accumulating for over 20 million years. These biological monuments represent construction projects that span geological time, built through the collaborative efforts of trillions of individual organisms working without blueprints or central planning. The mystery that fascinates marine biologists involves the remarkable coordination that allows reef ecosystems to function as integrated biological systems. The coral colonies communicate through chemical signals that travel through the water, coordinating reproductive cycles across entire reef systems. When environmental conditions are optimal, corals across hundreds of miles of reef can release their eggs and sperm simultaneously, creating underwater snowstorms of genetic material that ensure successful reproduction. The architectural complexity of coral reefs creates three-dimensional habitats that support biological diversity rivaling that of tropical rainforests. The limestone framework constructed by corals provides surfaces for algae and other organisms to colonize, while the complex topography creates countless niches for fish, crustaceans, mollusks, and other marine life. A single large coral colony can provide habitat for thousands of different species, creating biological apartment complexes of extraordinary sophistication. Reef-building corals pioneer new approaches to biological construction that solve fundamental engineering problems through elegant chemical processes. They must extract calcium carbonate from seawater that contains relatively low concentrations of the necessary minerals, concentrating these materials within specialized cells before secreting them as precisely structured skeletal elements. The process requires sophisticated biochemical machinery that can operate continuously for decades or centuries. The ecological engineering accomplished by coral reefs extends far beyond the construction of limestone structures. Reefs modify local current patterns, creating protected lagoons and channels that influence the distribution of nutrients and organisms across entire marine ecosystems. They serve as nurseries for countless species that depend on reef environments during critical stages of their life cycles, supporting food webs that extend far into surrounding ocean basins. Different species of corals specialize in different aspects of reef construction, creating biological cities with distinct neighborhoods optimized for specific environmental conditions. Brain corals develop massive, hemispherical colonies that can withstand strong wave action. Staghorn corals create branching structures that maximize surface area for photosynthesis. Table corals form flat, horizontal platforms that provide shelter for fish and other organisms seeking protection from currents and predators. The symbiotic relationships that power coral reef ecosystems represent some of the most sophisticated biological partnerships ever to evolve. Coral polyps maintain gardens of algae within their tissues, providing these photosynthetic partners with nutrients and protection while harvesting the sugars they produce. The metabolic integration between coral and algae is so complete that the partnership functions as a single biological entity. Though it represents the collaboration between organisms separated by billions of years of evolutionary history, coral reproduction requires extraordinary coordination between organisms that may be separated by vast distances across reef systems. Many coral species reproduce through synchronized spawning events that occur only once or twice per year, triggered by complex environmental cues including lunar cycles, water temperature, and tidal patterns. The timing must be precise, as eggs and sperm can survive for only brief periods in the open ocean before losing their viability. The construction materials used by corals demonstrate remarkable biomineralization capabilities that exceed the performance of many human-engineered materials. Coral skeletons combine strength, lightness, and flexibility in ways that allow them to withstand hurricane-force storms while continuing to grow and repair damage. The microstructure of coral limestone includes features that help dissipate wave energy and prevent catastrophic failure under extreme loading conditions. Reef ecosystems develop complex chemical communication networks that allow different species to coordinate their activities and respond collectively to environmental changes. Corals release chemical signals that attract beneficial organisms while deterring potential threats. Fish species use chemical cues to navigate through reef systems and locate appropriate habitat. The chemical ecology of reefs creates information landscapes where organisms can assess conditions and make behavioral decisions based on molecular messages. The geological impact of coral reef construction extends far beyond individual reef systems. Over millions of years, coral reefs have produced massive limestone formations that form entire mountain ranges and island chains. The accumulated skeletal remains of ancient reefs provide some of the most important fossil records of past climate conditions and evolutionary changes. Modern petroleum deposits often originated in ancient reef environments where organic matter accumulated in limestone formations. Climate regulation by coral reefs influences oceanic and atmospheric processes on regional and global scales. Reefs modify local temperature and humidity patterns, affecting weather systems and ocean circulation. The biological processes occurring within reef ecosystems influence the cycling of carbon, nitrogen, and other elements critical for global biogeochemical processes. Changes in reef health can have cascading effects on climate systems far from the reefs themselves. The vulnerability of coral reefs to environmental change highlights their sensitivity to conditions that have remained relatively stable for millions of years. Temperature increases of just a few degrees can disrupt the symbiotic relationships that power reef ecosystems, causing corals to expel their algal partners in events known as coral bleaching. Ocean acidification, caused by increased atmospheric carbon dioxide, makes it more difficult for corals to extract the minerals needed for skeleton construction. Yet, throughout their long history, coral reefs have demonstrated remarkable resilience and adaptability. They have survived ice ages, asteroid impacts, and massive volcanic eruptions that destroyed countless other ecosystems. Their ability to rebuild from small, surviving fragments has allowed reef systems to recover from devastating environmental changes and continue their construction projects across geological time. Only the coral polyps don't understand that they're building some of the largest biological structures ever created on Earth. They experience their construction activities not as architectural projects, but as basic metabolic processes, daily activities that happen to create limestone cities capable of supporting ecosystems more diverse than any terrestrial habitat. They have no awareness that their collaborative construction efforts are creating monuments to biological cooperation that will endure far longer than any civilization built by conscious minds. Only took a few 100 million years for simple marine animals to evolve into sophisticated biological architects. Only the patient accumulation of limestone secretions to create underwater cities that rival continents in their ecological impact. Only the endless collaboration between corals and algae to establish biological construction projects sophisticated enough to influence global climate systems and create habitats diverse enough to support the evolution of countless species, including those that will eventually develop consciousness sufficient to appreciate the architectural achievements of their reef-building predecessors in the ancient seas. The Great Emergence begins with a single green cell crawling from the shallow margins of an ancient sea onto the naked rock of a world that has never known the touch of life. 450 million years ago, the continents stretch barren and silent under alien skies, vast deserts of stone and sand where no footprint has ever fallen, no root has ever penetrated the sterile soil. Yet, in this seemingly impossible landscape, life prepares to attempt its most audacious colonization project, the conquest of dry land. The pioneers are not grand or heroic by any measure. They are microscopic green algae, simple pond scum that has learned to tolerate brief periods of desiccation when tidal pools evaporate under the sun. These humble organisms possess no eyes to see the vast territories awaiting colonization, no limbs to carry them across the hostile landscape, no consciousness to appreciate the magnitude of their undertaking. They simply follow the relentless logic of reproduction and dispersal, spreading wherever chemistry and physics will allow them to survive. The challenges facing terrestrial colonization seem insurmountable to organisms adapted for aquatic life. Water, the universal solvent that enables all biological chemistry, is scarce and unreliable on land. Temperatures fluctuate wildly between day and night, creating thermal stresses unknown in the buffered environment of the oceans. Ultraviolet radiation, filtered by seawater in marine environments, strikes the land surface with intensity that can shatter the delicate molecular machinery of life. Yet, these early terrestrial pioneers begin to develop solutions to the fundamental problems of life on dry land through innovations that will define terrestrial biology for the next 500 million years. They evolve waxy coatings that prevent water loss, creating the first biological raincoats. They develop structural compounds like lignin that provide support without the buoyancy of water, engineering the molecular frameworks that will eventually support forest canopies reaching hundreds of feet into the sky. The mystery that confounds botanists involves the rapidity with which complex terrestrial adaptations appear in the fossil record. Within a few tens of millions of years, simple algal mats give rise to sophisticated vascular plants with roots, stems, leaves, and reproductive structures specifically adapted for terrestrial life. The evolutionary innovations required for this transition involve fundamental changes in cellular architecture, metabolism, and reproductive biology that should require much longer time periods to evolve. Fungi emerge as unexpected allies in the terrestrial colonization project, forming partnerships with early plants that provide essential services neither organism could accomplish alone. The fungal networks that extend through soil create vast underground communication systems that dwarf any human telecommunications network. These mycorrhizal associations allow plants to access nutrients and water across much larger areas than their roots could reach independently, while fungi receive sugars and other organic compounds they cannot produce through photosynthesis. The first terrestrial ecosystems develop around freshwater streams and lakes where moisture remains relatively abundant. Simple bryophytes, the ancestors of modern mosses, create living carpets that help stabilize soil and retain moisture for other colonizing organisms. These pioneer communities establish the ecological foundations for more complex terrestrial ecosystems, creating microenvironments where humidity and temperature remain within tolerable ranges for organisms still adapting to terrestrial conditions. Primitive vascular plants begin to experiment with vertical growth strategies that allow them to compete for access to sunlight in increasingly crowded terrestrial communities. The evolution of lignified tissues enables plants to construct self-supporting towers that rise above their neighbors, creating the first forests in Earth's history. These early woodlands transformed the terrestrial landscape from barren rock to complex three-dimensional habitats that provide niches for countless other organisms. The chemical engineering required for terrestrial plant life involves solving problems that have no aquatic equivalents. Plants must extract water and minerals from soil through root systems that can penetrate rock and navigate through complex subsurface environments. They must transport these materials upward through vascular systems that can function against gravity across distances measured in hundreds of feet. They must regulate gas exchange through specialized pores that balance the need for carbon dioxide uptake with the risk of water loss. Reproductive strategies for terrestrial plants require fundamental innovations in the protection and dispersal of genetic material. Unlike marine organisms that can rely on water for gamete transport, terrestrial plants must develop mechanisms for moving sperm to eggs across dry environments. Early solutions include wind-dispersed spores and increasingly sophisticated systems for protecting developing embryos from desiccation and temperature extremes. The colonization of terrestrial environments creates new ecological opportunities for organisms willing to abandon the security of aquatic habitats. Arthropods follow plants onto land, developing respiratory systems that extract oxygen directly from air rather than from water. These early terrestrial animals must solve the same fundamental problems of water conservation and structural support that challenge plants, leading to evolutionary innovations in exoskeleton design and metabolic efficiency. Soil development accelerates as terrestrial ecosystems become established, creating complex chemical environments where biological and geological processes interact in unprecedented ways. Plant roots and fungal networks break down rock through both mechanical and chemical weathering, while organic matter from dead plants and animals accumulates to form the rich, living substrates that will support increasingly complex terrestrial communities. The atmospheric chemistry begins to change as terrestrial photosynthesis supplements oxygen production from marine algae and cyanobacteria. Forests remove carbon dioxide from the atmosphere while releasing oxygen and water vapor, influencing global climate patterns and creating feedback loops that affect both terrestrial and marine ecosystems. The emergence of life on land marks the beginning of biological climate regulation on a planetary scale. Early terrestrial animals must develop entirely new sensory systems adapted for navigation and communication in aerial environments. Sound travels differently through air than through water, creating opportunities for acoustic communication across much larger distances. Light environments become more complex as plant canopies create intricate patterns of shade and illumination that can be exploited for camouflage and signaling. The diversification of terrestrial ecosystems proceeds with remarkable rapidity as organisms discover and exploit the countless niches available in three-dimensional forest environments. Different plant species specialize for life in different light regimes, from the bright canopy to the shaded forest floor. Animals evolve for life in the soil, on plant surfaces, within plant tissues, and in the aerial spaces between vegetation. Predator-prey relationships on land develop dynamics very different from those in aquatic environments. The complex topography of terrestrial ecosystems provides countless opportunities for concealment and ambush, while the acoustic properties of air enable long-distance detection of both predators and prey. The evolution of flight will eventually add a vertical dimension to terrestrial predation that has no aquatic equivalent. Chemical communication becomes increasingly important in terrestrial environments where visual and acoustic signals can be blocked by vegetation. Plants and animals develop sophisticated systems for producing and detecting airborne chemical signals that carry information about species identity, reproductive status, and environmental threats. The chemical ecology of terrestrial ecosystems creates information landscapes of extraordinary complexity. Only the pioneering organisms don't understand that they're establishing the biological foundations for every terrestrial ecosystem that will ever exist. They experience their terrestrial adaptations not as revolutionary innovations, but as incremental solutions to immediate survival challenges. small modifications that happen to enable life in environments that have remained sterile since the planet's formation. They have no awareness that their colonization efforts are creating the terrestrial habitats that will eventually support the evolution of consciousness complex enough to study its own origins. Only took a few tens of millions of years for simple aquatic algae to evolve into complex terrestrial plants and animals. Only the patient development of terrestrial adaptations to transform barren continents into living landscapes. Only the endless experimentation with biological solutions to terrestrial survival challenges to create ecosystems sophisticated enough to support the evolution of organisms capable of appreciating the magnitude of life's conquest of dry land in the patient history of biological innovation written in the fossil record of ancient terrestrial communities. Beneath the forest floor, in the darkness where no sunlight penetrates and no eyes have evolved to see, the most sophisticated communication network in Earth's history begins to take shape. Fungal threads, finer than spider silk, weave through soil and around plant roots, creating underground highways that stretch for thousands of miles beneath a single forest canopy. These mycorrhizal networks connect trees across vast distances, allowing chemical conversations that will persist for centuries and coordinate the behavior of entire ecosystems. The individual fungal filaments are almost impossibly delicate, each one thinner than a human hair and composed of single cells arranged end-to-end like microscopic train cars. Yet when billions of these threads work together, they create underground networks of staggering complexity and power. A single cubic inch of forest soil may contain hundreds of miles of fungal filaments, weaving through the spaces between soil particles in patterns that maximize contact with plant roots while minimizing energy expenditure. The trees above, apparently independent organisms competing for light and space in the forest canopy, are actually participants in vast underground parliaments, where resources are shared according to rules that ecologists are only beginning to understand. When a massive Douglas fir needs phosphorus for spring growth, chemical signals travel through the fungal network to distant parts of the forest where other trees contribute to the collective resource pool. When a young seedling struggles to survive in deep shade, established trees channel nutrients to the struggling plant through the underground networks, investing in the forest's future. Scientists studying these forest communication systems have discovered that trees can recognize their own offspring through chemical signatures transmitted via fungal networks. Mother trees provide preferential support to their genetic descendants, channeling resources to their seedlings while providing less assistance to unrelated plants. This underground nepotism creates family networks within forests that can persist for hundreds of years, with multiple generations of trees maintaining genetic alliances through their fungal partners. The mystery that confounds forest ecologists involves the remarkable intelligence displayed by these networks despite the absence of any centralized control system. Trees and fungi possess no brains or nervous systems, yet their underground collaborations demonstrate sophisticated decision-making capabilities that rival the cognitive processes of animal minds. How do these simple organisms coordinate complex resource-sharing behaviors across spatial scales that extend for miles and temporal scales that span centuries? The chemical vocabulary used by underground forest networks includes thousands of different molecular signals that carry specific information about resource availability, pathogen threats, and environmental stresses. When a tree is attacked by insects, it releases chemical alarm signals that travel through the fungal network to warn distant neighbors, allowing them to begin producing defensive compounds before the threat arrives. These early warning systems operate faster and more efficiently than any telecommunications technology humans have ever developed. Different tree species contribute distinct expertise to the underground economy, creating biological markets where various forms of value are exchanged according to supply and demand dynamics that economists are only beginning to analyze. Evergreen trees provide steady supplies of carbon throughout the year, while deciduous trees contribute seasonal pulses of nutrients when their leaves decompose. Young trees offer future growth potential, while ancient trees provide stability and resource reserves that sustain the network through difficult periods. The architecture of fungal networks follows mathematical principles that optimize information flow while minimizing energy costs. Network topology studies reveal that fungal systems develop hub-and-spoke configurations remarkably similar to airline route maps or internet routing protocols. Major trees serve as network hubs that coordinate information flow across large regions, while smaller connecting fungi provide redundant pathways that maintain network integrity when individual components fail. Seasonal rhythms coordinate underground forest activities according to biological calendars that have been refined over millions of years of evolutionary experimentation. Spring nutrient exchanges support the energy demands of new growth, while autumn resource sharing helps trees prepare for winter dormancy. The timing of these exchanges requires precise biochemical coordination between species that may be separated by hundreds of yards and evolutionary histories spanning tens of millions of years. The underground economy operates according to principles of reciprocal altruism that ensure long-term network stability while accommodating the individual needs of participating organisms. Trees that receive resources during times of stress typically repay their debts when conditions improve, creating credit systems that maintain forest-wide cooperation across multiple growing seasons. Default rates are extremely low, suggesting that evolutionary pressures have selected for biochemical mechanisms that enforce contractual obligations. Research using radioactive carbon tracers has revealed that nutrients can travel through fungal networks from one tree to another in as little as 24 hours, creating resource distribution systems that respond to forest needs with remarkable speed and precision. During drought conditions, trees with access to reliable water sources can share moisture with stressed neighbors through underground networks, preventing large-scale forest mortality during extreme environmental events. The defensive capabilities of forest networks extend far beyond early warning systems to include coordinated chemical warfare against pathogens and herbivores. When fungal networks detect the presence of harmful bacteria or viruses, they coordinate the production of antimicrobial compounds across entire forest ecosystems. These collective immune responses can eliminate threats that would overwhelm individual trees, creating forest-wide resistance to diseases that might otherwise cause widespread mortality. Competitive dynamics within forest networks create underground markets where trees bid for access to limited resources through chemical negotiations that can last for weeks or months. Trees experiencing resource stress increase their chemical offers for nutrients, while well-supplied trees can afford to be selective about which neighbors receive assistance. These market mechanisms ensure efficient resource allocation while maintaining the cooperation necessary for network stability. The information processing capabilities of forest networks rival those of simple neural systems. Despite operating through diffusion-based chemical signals rather than electrical impulses, trees can integrate information from multiple sources, weigh different response options, and implement coordinated strategies that maximize collective fitness. The computational power distributed throughout these underground systems may represent the largest biological information processing networks on Earth. Climate regulation by forest networks operates on regional and global scales through coordinated transpiration patterns that influence local weather systems. When underground networks detect approaching drought conditions, they coordinate reductions in water use across entire forest ecosystems, conserving moisture reserves while minimizing stress on individual trees. These collective responses to environmental challenges demonstrate ecosystem-level intelligence that emerges from the interactions of countless individual organisms. Succession dynamics in forests are guided by underground networks that can persist for centuries, providing institutional memory that spans multiple forest generations. When mature trees die and fall, their fungal partners help coordinate the establishment of replacement vegetation, ensuring continuity in forest structure and function. These underground succession plans operate according to ecological wisdom accumulated over hundreds of years of forest experience. The global extent of forest networks suggests that terrestrial ecosystems are connected by underground communication systems that span continents. Fungal spores travel on wind currents between distant forests, potentially creating genetic and informational connections between ecosystems separated by thousands of miles. The implications of these intercontinental forest networks for global ecosystem dynamics and climate regulation remain largely unexplored. Only the trees and fungi don't understand that they're creating the most sophisticated biological communication networks in Earth's history. They experience their underground collaborations not as technological innovations, but as basic metabolic processes. Chemical exchanges that happen to create information systems more complex than any human telecommunications network. They have no awareness that their resource-sharing activities are establishing the ecological foundations for forest ecosystems capable of regulating global climate and supporting biological diversity, rivaling that of tropical coral reefs. Only took a few 100 million years for simple mycorrhizal associations to evolve into planet-spanning underground communication networks. Only the patient development of biochemical cooperation to create forest ecosystems capable of collective intelligence and coordinated environmental management. Only the endless refinement of chemical communication systems to establish biological networks sophisticated enough to support terrestrial ecosystems capable of housing the consciousness contemplating their own evolutionary origins in the hidden underground archives of fungal memory. The great dynasties rise from the earth with a thunder that echoes across 200 million years of geological time. The dinosaurs emerge not as the monsters of popular imagination, but as the planet's most successful experiment in biological governance, establishing civilizations that will endure 65 times longer than humans have existed. In the warm, humid world of the Mesozoic era, these remarkable creatures create societies of unprecedented sophistication, developing technologies of bone and muscle that allow them to dominate every terrestrial environment from polar forests to equatorial deserts. The first dinosaurs appear in the fossil record as modest creatures no larger than house cats, distinguished from their archosaur relatives mainly by subtle differences in hip structure and leg positioning. Yet, these seemingly minor anatomical innovations unlock extraordinary evolutionary potential, allowing dinosaurs to experiment with body plans and ecological strategies that will eventually produce organisms ranging from tiny feathered creatures to titans weighing as much as 10 elephants. The diversity they achieve surpasses that of any other group of terrestrial vertebrates in Earth's history. Sauropods pioneer biological engineering solutions that push the physical limits of terrestrial life to their absolute boundaries. Argentinosaurus reaches lengths of over 100 feet and weights approaching 100 tons, requiring anatomical innovations that solve fundamental problems of structural support and resource distribution. Their hollow bones reduce weight while maintaining strength through principles that modern engineers are only beginning to understand. Their cardiovascular systems develop multiple hearts and specialized blood pressure regulation mechanisms that allow circulation in bodies tall enough to require elevators in human buildings. The mystery that captivates paleontologists involves the sophisticated social behaviors that emerge repeatedly throughout dinosaur evolution. Fossil evidence suggests that many species engaged in complex parental care, with adults constructing elaborate nests and providing food for their offspring for extended periods after hatching. Dinosaur trackways preserve evidence of coordinated group movements across vast distances, indicating that some species engaged in migrations rivaling those of modern wildebeest or caribou. Theropods evolve into the most sophisticated predators ever to walk the earth, developing hunting strategies that combine individual intelligence with group coordination. Velociraptors hunt in packs, using communication systems based on visual signals and vocalizations that allow coordinated attacks on prey much larger than any individual predator. Their sickle-shaped claws represent biological weapons of extraordinary precision, evolved for delivering fatal wounds with surgical accuracy. The communication systems developed by dinosaurs appear to rival those of modern birds and mammals in their complexity and sophistication. Parasaurolophus and other hadrosaurs evolve elaborate cranial crests that function as biological trumpets, capable of producing low-frequency calls that can travel for miles through dense forest environments. These acoustic communication networks allow dinosaur communities to coordinate their activities across territories spanning hundreds of square miles. Ceratopsians develop some of the most elaborate display structures in the history of terrestrial life, with skull ornamentation that rivals the architectural achievements of any human civilization. Triceratops creates massive bone shields decorated with spikes and ridges that serve both defensive and communicative functions. The energy investments required to grow and maintain these structures suggest that social signaling was critically important in dinosaur societies, perhaps determining access to mates, territories, and resources. The nesting sites discovered by paleontologists reveal dinosaur reproductive strategies of remarkable sophistication, with evidence of communal nesting areas where multiple females laid their eggs in carefully constructed colonies. Some species appear to have engaged in cooperative brood care, with adults taking turns incubating eggs and defending nests from predators. These behaviors require social coordination mechanisms that approach the complexity of modern bird and mammal societies. Dinosaur thermoregulation represents one of the most successful solutions to the challenges of maintaining stable body temperature in large terrestrial animals. Evidence suggests that many dinosaurs were neither cold-blooded like modern reptiles nor warm-blooded like modern mammals, but rather employed intermediate strategies that combined the best features of both approaches. This metabolic innovation allowed them to remain active across a much wider range of environmental conditions than purely cold-blooded animals could tolerate. The global distribution of dinosaur fossils demonstrates that these animals successfully colonized every continent and adapted to virtually every terrestrial environment available during the Mesozoic era. Dinosaur remains have been discovered in polar regions where they lived through months of winter darkness, in desert environments where water was scarce, and in dense forest ecosystems where they competed with countless other species for resources. Their ecological adaptability exceeded that of any other group of large terrestrial animals. Feathers emerged during dinosaur evolution not initially for flight, but for display and temperature regulation, creating some of the most beautiful biological structures ever to evolve. Small theropods develop elaborate plumage that rivals modern birds in its complexity and coloration. These early experiments with feathered ornamentation established the foundation for powered flight, though the original function appears to have been social signaling and thermal management rather than aerial locomotion. The largest dinosaur societies may have included millions of individuals organized into complex hierarchical structures that determined access to feeding areas, nesting sites, and mates. Fossil evidence of massive bone beds suggests that some dinosaur species engaged in migrations involving entire populations, with individuals of different ages and sizes traveling together across continental distances. The coordination required for such movements implies communication and organizational capabilities that rival those of modern mammal societies. Dinosaur parental care appears to have been more sophisticated than that of most modern reptiles, with evidence that many species engaged in prolonged care of their offspring. Some dinosaur nests contain fossils of adults positioned as if brooding their eggs, while juvenile fossils are often found in association with adults in ways that suggest extended family groups. These behavioral patterns require emotional and cognitive capabilities that challenge traditional assumptions about reptilian intelligence. The architectural achievements of dinosaur civilizations, while built from bone and muscle rather than stone and metal, rival those of any subsequent terrestrial organisms. Sauropod communities create clearings in forests through their feeding activities, engineering landscape modifications that persist for thousands of years. Their trampling creates networks of pathways that channel water flow and influence plant succession patterns across entire ecosystems. Predator-prey relationships in dinosaur ecosystems develop extraordinary sophistication as both hunters and hunted evolve increasingly advanced strategies for success. Some predators appear to have used tools, manipulating environmental features to their advantage during hunts. Prey species develop early warning systems based on acoustic and chemical communication that allow rapid response to predator threats across large areas. The end comes suddenly, written in a thin layer of clay enriched with extraterrestrial iridium that marks the boundary between the Mesozoic and Cenozoic eras. In perhaps a few years, certainly less than a few thousand, the great dinosaur civilizations collapse as asteroid impact and volcanic activity transform Earth's climate beyond the tolerance limits of most large terrestrial organisms. The titans that have ruled the land for over 160 million years disappear from the fossil record with startling finality. Yet, the dinosaur legacy persists in the birds that fill modern skies, direct descendants that carry dinosaur genes and behaviors into the present day. Their sophisticated social behaviors, elaborate communication systems, and remarkable intelligence represent living connections to the greatest terrestrial civilizations in Earth's history. The songs of modern birds echo the acoustic landscapes of dinosaur societies that once coordinated their activities across continents. Only the dinosaurs don't understand that they're creating the most enduring terrestrial civilizations in Earth's history. They experience their social behaviors not as political innovations, but as instinctive responses to environmental challenges, behavioral patterns that happen to create societies more stable and long-lasting than any human civilization. They have no awareness that their biological technologies are establishing organizational principles that will influence terrestrial ecosystems for millions of years after their extinction. Only took 200 million years for simple archosaurs to evolve into the most sophisticated terrestrial societies in Earth's history. Only the patient refinement of social behaviors and biological technologies to create civilizations that dominated terrestrial ecosystems longer than any other group of organisms. Only the endless experimentation with cooperative strategies and communication systems to establish social structures sophisticated enough to coordinate the activities of millions of individuals across continental scales, creating biological civilizations that achieved organizational complexity rivaling that of any conscious society in the long history of life's experiments with terrestrial governance. In the shadows of the great lizard dynasties, small, warm-blooded creatures with soft fur and beating hearts begin their patient apprenticeship in survival. These early mammals scurry through underbrush and burrow beneath fallen logs, living lives measured in heartbeats rather than geological epochs, inheriting a world where size means death and invisibility ensures survival. They are the quiet inheritors, developing technologies of stealth and efficiency that will serve them well when the thunder of dinosaur footsteps finally falls silent across the ancient continents. The first mammals appeared during the late Triassic, evolving alongside the earliest dinosaurs but pursuing radically different strategies for terrestrial success. While dinosaurs experiment with gigantism and ecological dominance, mammals perfect the arts of concealment and metabolic efficiency. They remain small by necessity, most species weighing less than a modern house cat, developing nocturnal lifestyles that allow them to exploit resources unavailable to their larger, cold-blooded contemporaries. Fur emerges as one of the most successful biological technologies ever developed, providing insulation that allows mammals to maintain stable body temperatures across environmental conditions that would incapacitate reptilian competitors. This thermal independence frees mammals from the constraints of external temperature regulation, enabling activity during cool nights when dinosaurs must remain torpid. The metabolic strategies that support this thermal autonomy require sophisticated cardiovascular and respiratory systems that operate at efficiencies unknown in earlier vertebrate lineages. The mystery that intrigues mammalian paleontologists involves the remarkable conservatism of early mammal body plans. For over 100 million years, most mammal species remain small, generalized creatures that show relatively little morphological diversity compared to the explosive radiation of dinosaur forms. Yet this apparent stagnation conceals profound innovations in physiology, behavior, and reproductive biology that will prove crucial when environmental conditions finally favor mammalian expansion. Lactation represents perhaps the most revolutionary innovation in vertebrate reproductive biology, allowing mammalian mothers to provide customized nutrition to their offspring for extended periods after birth. This biological technology requires sophisticated hormonal control systems and metabolic adaptations that enable females to convert their own body resources into perfectly formulated infant food. The evolutionary advantages of prolonged parental care become apparent when environmental conditions place premium values on behavioral flexibility and learning capacity. Early mammalian societies develop complex social structures despite their small size and secretive lifestyles. Fossil evidence suggests that some species engaged in cooperative burrow construction and shared parental responsibilities within extended family groups. These early experiments in mammalian cooperation establish behavioral foundations that will prove essential when larger mammalian species eventually evolve community structures rivaling those of dinosaur societies. The sensory capabilities of early mammals exceed those of most contemporary reptiles, particularly in areas of olfaction and acoustic communication. Mammalian ears develop extraordinary sensitivity to high-frequency sounds, enabling communication and predator detection capabilities that function effectively in the acoustic environments of dense vegetation. Their chemical sensory systems become sophisticated enough to gather detailed information about individual identity, reproductive status, and territorial boundaries through scent-marking behaviors. Parental care strategies in early mammals require extended energy investments that exceed those of egg-laying reptiles, but provide corresponding advantages in offspring survival and behavioral development. Young mammals undergo prolonged learning periods during which they acquire essential survival skills through observation and practice rather than relying entirely on genetically programmed behaviors. This emphasis on learned rather than innate responses creates adaptive flexibility that serves mammalian lineages well in rapidly changing environments. The metabolic demands of mammalian thermoregulation require dietary strategies that maximize energy extraction from available food sources. Early mammals develop increasingly sophisticated dentition that allows efficient processing of insects, seeds, and other concentrated energy sources. Their digestive systems evolve specialized features for extracting maximum nutritional value from small quantities of high-quality food, enabling survival in ecological niches where larger animals cannot obtain sufficient resources. Burrowing technologies reach new levels of sophistication in mammalian lineages, with some species constructing elaborate underground tunnel systems that provide protection from predators while maintaining access to food resources. These subterranean architectural projects require coordination between multiple individuals and represent some of the most complex construction behaviors seen in vertebrates prior to the evolution of human technology. The nervous systems of early mammals undergo significant evolutionary modifications that enhance their capacity for behavioral flexibility and environmental responsiveness. Brain regions associated with learning and memory expand, relative to those controlling purely instinctive behaviors, creating neural architectures that support increasingly complex behavioral repertoires. These neurological innovations establish the foundations for the cognitive capabilities that will distinguish mammals from other vertebrate groups. Reproductive timing in mammalian species becomes increasingly sophisticated as they develop hormonal mechanisms that coordinate breeding cycles with seasonal resource availability. Unlike reptiles that may reproduce opportunistically when conditions permit, mammals evolve predictive capabilities that allow them to anticipate optimal breeding conditions and prepare for reproductive events well in advance. Social communication in early mammalian communities involves complex combinations of acoustic, chemical, and tactile signals that convey detailed information about individual identity and intentions. These communication systems operate effectively in the dense vegetation and low-light conditions where mammals conduct most of their activities, creating information networks that support coordinated group behaviors despite the limitations of terrestrial sensory environments. The end Cretaceous extinction event that eliminates non-avian dinosaurs creates unprecedented opportunities for mammalian diversification. Within a few million years of the extinction boundary, mammalian species begin exploring ecological niches that have been closed to them for over 100 million years. Body sizes increase dramatically as mammals experiment with herbivorous lifestyles that take advantage of plant resources no longer consumed by large dinosaurian herbivores. The adaptive radiations that follow the dinosaur extinction demonstrate the evolutionary potential that has been accumulating in mammalian lineages throughout their long period of ecological marginalization. Sophisticated physiological and behavioral capabilities that evolved for survival in restricted niches prove remarkably well suited for exploitation of the diverse ecological opportunities available in post-extinction ecosystems. Mammalian societies begin developing organizational complexities that rival those of their dinosaurian predecessors, with some species forming large herds that migrate across continental distances in search of seasonal resources. The social coordination mechanisms required for these movements draw upon communication and leadership capabilities that evolved during millions of years of small group cooperation in secretive mammalian communities. The cognitive capabilities that distinguish mammals from most other vertebrates become increasingly apparent as species evolve complex problem-solving abilities and behavioral innovations that allow rapid adaptation to novel environmental challenges. These mental faculties, refined through millions of years of survival in dangerous and unpredictable environments, provide mammals with adaptive advantages that prove crucial in the rapidly changing post-extinction world. Technological innovations in mammalian societies begin with simple tool use and environmental manipulation, but rapidly expand to include increasingly sophisticated behaviors that modify landscapes and influence ecosystem dynamics. Some mammalian species learn to cultivate preferred plant species through selective browsing and seed dispersal, creating early examples of agricultural practices that will reach full development in later human societies. Only the early mammals don't understand that they're developing the biological and behavioral foundations for the most cognitively sophisticated civilizations in Earth's history. They experience their survival innovations not as preparation for future dominance, but as immediate responses to environmental pressures, behavioral adaptations that happen to establish capabilities that will prove crucial when opportunities for expansion finally arise. Only took 160 million years for small, secretive creatures to develop the physiological and behavioral capabilities necessary for global ecological dominance. Only the patient refinement of mammalian technologies during their long apprenticeship in survival to create organisms capable of supporting nervous systems sophisticated enough to eventually develop consciousness, language, and technological civilization. Only the endless experimentation with behavioral flexibility and social cooperation to establish the cognitive foundations for species capable of studying their own evolutionary origins and appreciating the patient persistence of their mammalian ancestors in the dangerous shadows of the ancient world. Before human memory begins, before consciousness learns to contemplate its own origins, before language develops words for time itself, Earth hosts countless experiments in organized complexity that leave only the faintest traces in stone. The planet breathed slowly through 4 billion years of biological innovation, each inhalation bringing new forms of life, each exhalation carrying away entire civilizations that flourished for spans of time that reduce human history to the briefest flicker of geological possibility. The ancient archives preserved in sedimentary rock tell stories of societies that dwarf human achievements in both scale and duration. Stromatolites built by bacterial communities create limestone monuments that persist for billions of years, architectural achievements that make the pyramids seem like temporary sandcastles. Coral reefs construct underwater cities that support biological diversity exceeding that of any terrestrial ecosystem. Collaborative projects that continue for millions of years without pause or central planning. In layers of shale and limestone, paleontologists discover evidence of social behaviors that challenge assumptions about the cognitive capabilities required for complex organization. Dinosaur nesting colonies suggest reproductive cooperation across multiple generations. Fossil trackways preserve records of coordinated migrations involving millions of individuals moving in formation across continental distances. These traces hint at organizational sophistication that operated without written language, permanent architecture, or conscious reflection. The timescales of pre-human civilizations stretch human comprehension beyond its comfortable limits. Cyanobacteria maintain their photosynthetic civilizations for over 2 billion years, a period longer than complex life has existed on Earth. Dinosaur societies persist for 160 million years, demonstrating political stability that no human government has approached. Even the briefest experiments in biological organization often endure for periods measured in millions of years. The mystery that haunts students of deep time involves the apparent intelligence displayed by organisms that possess no nervous systems recognizable to neuroscientists. Forest networks coordinate resource distribution across hundreds of square miles through chemical communication systems that operate more efficiently than human telecommunications. Bacterial communities make collective decisions about metabolism and reproduction that benefit entire ecosystems. Social insects construct architectural marvels that require precise coordination among millions of individuals. Communication technologies developed by pre-human civilizations often exceed human capabilities in their sophistication and reliability. Whales develop acoustic languages that can transmit complex information across entire ocean basins. Plants create chemical vocabularies that include thousands of distinct molecular signals. Fungi establish underground networks that maintain information flow across centuries, creating biological libraries that preserve ecological knowledge across multiple forest generations. The engineering achievements of biological civilizations demonstrate solutions to technical problems that human technology has not yet mastered. Bird navigation systems integrate information from magnetic fields, star positions, and landscape features with precision that surpasses electronic guidance systems. Bacterial motors achieve energy conversion efficiencies approaching theoretical limits. Insect flight mechanics employ aerodynamic principles that aircraft designers are only beginning to understand. Ecological management by pre-human civilizations creates environmental stability that persists across geological time periods. Coral reef communities regulate ocean chemistry in ways that support biological diversity for millions of years. Forest ecosystems develop nutrient cycling systems that maintain soil fertility across centuries without external inputs. Grassland communities engineer fire regimes that prevent ecological succession while maintaining habitat diversity. The social structures developed by biological civilizations often demonstrate organizational principles that human societies struggle to implement. Ant colonies achieve perfect division of labor without unemployment or exploitation. Bee societies make collective decisions through democratic processes that ensure optimal outcomes for entire communities. Termite colonies construct climate-controlled cities that maintain stable temperature and humidity without external energy sources. Reproductive strategies in pre-human civilizations ensure genetic diversity and population stability across environmental fluctuations that would collapse most human societies. Many species develop mating systems that prevent inbreeding while maintaining cooperative social structures. Others evolve reproductive timing mechanisms that coordinate breeding cycles with resource availability across multi-year environmental cycles. The cultural transmission mechanisms used by biological civilizations preserve essential information across multiple generations without written records. Songbirds maintain acoustic traditions that persist for hundreds of years. Primates develop tool use techniques that spread through populations and persist across generations. Whales preserve song traditions that may carry ecological information accumulated over centuries of oceanic experience. Conflict resolution in pre-human civilizations often achieves outcomes that minimize energy expenditure while maintaining social stability. Many species develop ritualized combat behaviors that establish dominance hierarchies without causing serious injury. Others evolve chemical communication systems that allow negotiation of territorial boundaries without physical confrontation. These biological diplomatic protocols maintain peace across time periods that exceed the duration of human civilization. The mathematical principles underlying biological organization demonstrate computational capabilities that operate without conscious calculation. Optimal foraging strategies in animal societies follow algorithms that maximize energy return while minimizing risk. Plant growth patterns conform to geometric principles that optimize light capture and structural stability. Social insect construction projects implement architectural solutions that minimize material usage while maximizing structural strength. Resource management systems developed by biological civilizations achieve sustainability that human societies have yet to match. Predator-prey relationships maintain stable population dynamics across thousands of generations. Nutrient cycling in natural ecosystems operates at near-perfect efficiency with minimal waste production. Energy flow through biological communities approaches thermodynamic optimality while supporting remarkable diversity. The sensory capabilities developed by pre-human civilizations often detect environmental information unavailable to human perception. Many animals sense magnetic fields, electrical currents, infrared radiation, and ultrasonic vibrations. These expanded sensory capabilities provide access to information about environmental conditions, resource availability, and threat detection that exceed human awareness even with technological assistance. Memory systems in biological civilizations preserve information across timescales that dwarf human historical records. Tree rings maintain environmental data for thousands of years. Genetic information carries instructions refined across millions of years of evolutionary experience. Ecosystem structures preserve ecological relationships that have persisted since before human ancestors developed bipedal locomotion. The geographic scales of pre-human civilizations encompass territories that exceed any human political entity. Mycorrhizal networks extend across entire continents, connecting forest ecosystems separated by thousands of miles. Migratory species maintain social connections across hemispheres, coordinating reproductive and foraging activities across global distances. Ocean currents transport biological communities around the planet, creating marine civilizations that span multiple ocean basins. Yet all these civilizations, for all their sophistication and endurance, lack the capacity for self-reflection that emerges with human consciousness. They operate according to genetic programs and environmental responses, creating remarkable complexity without awareness of their own achievements. They build, communicate, cooperate, and compete with extraordinary sophistication while remaining unconscious of the significance of their actions. Only humans develop the cognitive capabilities necessary to study and appreciate the biological civilizations that preceded them. Only human consciousness becomes complex enough to recognize the remarkable achievements of stromatolite builders, reef constructors, forest managers, and social insects. Only human societies develop technologies that can detect and analyze the traces of ancient biological complexity preserved in the geological record. The emergence of human consciousness represents a new phase in Earth's long experiment with organized complexity, the first time that biological civilization becomes aware of itself and its history. Human minds can contemplate the 4-billion-year story of life's increasing sophistication, appreciating achievements that their creators could never understand. Human science can detect the subtle traces of ancient biological technologies preserved in rocks older than multicellular life. Only took 4 billion years for unconscious biological processes to evolve conscious minds capable of studying their own origins. Only the patient accumulation of biological complexity to create organisms sophisticated enough to discover and appreciate the civilizations that preceded them. Only the endless experimentation with organized complexity to produce consciousness, capable of recognizing that human civilization represents merely the latest chapter in Earth's long history of biological innovation, continuing experiments in cooperation and communication that began with the first bacterial communities in the ancient seas of deep time. The ancient seas grow quiet now, their chemical conversations settling into the rhythms of deep time. Somewhere in the darkness beneath kilometers of sediment and stone, the first bacterial cities sleep in their limestone tombs, their molecular conversations reduced to whispers in the rock. The protocols they established for cellular cooperation continue in every living thing, written into the genetic constitution of complexity itself. The oxygen they released still fills the atmosphere, each breath carrying molecules that once passed through cyanobacterial cells when the Earth was young and the continents were bare. Their waste product has become the foundation of consciousness, the chemical prerequisite for every thought that has ever emerged in any mind. The revolution they began in the ancient oceans continues in the mitochondria that power these very words. Forest networks pulse quietly beneath sleeping trees, their fungal filaments carrying nutrients and information through underground pathways that will persist long after the human societies studying them have crumbled to dust. The diplomatic protocols they developed for resource sharing across species boundaries operate without treaties or conscious negotiation, managing ecosystems through chemical agreements refined across millions of years of collaboration. Coral polyps continue their patient construction projects in tropical seas, adding limestone to reefs that began growing before human ancestors descended from the trees. Each night, they extend their tiny arms to capture plankton. Each day, they provide sugars to their algal partners, maintaining partnerships older than vertebrate life on land. Their cities grow grain by grain, following architectural principles discovered in the early experiments with multicellular life. The songs of birds carry genetic echoes of dinosaur civilizations that coordinated their activities across continents for longer than mammals have existed. Each dawn chorus recalls acoustic landscapes that filled Mesozoic forests when flowering plants were evolutionary novelties and grass had not yet been invented. The intelligence that guides their complex behaviors emerged from nervous systems refined during the longest-lasting terrestrial civilizations in Earth's history. Somewhere in the deepest ocean trenches, bacteria still process chemicals in ways that predate photosynthesis by billions of years. They maintain the ancient biochemistry that powered the first organized communities, creatures so alien to modern life that they seem like visitors from another planet. Yet they are the eldest citizens of Earth, the inheritors of the original chemical wisdom that made all subsequent complexity possible. The planetary conversation continues in frequencies too slow for human perception, chemical signals that travel through rock and ocean, genetic information that flows between organisms separated by vast evolutionary distances. The protocols for biological cooperation established in the earliest bacterial communities still govern the cellular negotiations that maintain every complex organism, including the human societies that have learned to study their own origins. Time moves differently in the deep rhythms of geological change, where millions of years pass like seasons in the patient calendar of planetary evolution. The civilizations that rose and fell before human consciousness emerged operated on these slower timescales, building and communicating and governing themselves through processes that required eons to complete their cycles. The Earth sleeps fitfully through its long experiment with organized complexity, dreaming perhaps of the bacterial cities that once covered its sea floors, the coral reefs that engineered its ocean chemistry, the forest networks that still regulate its climate, the dinosaur societies that demonstrated the possibilities of biological governance on continental scales. Each geological epoch brings new forms of organization, new experiments in cooperation, new solutions to the ancient problems of survival and reproduction. In the fossil record preserved in sedimentary rocks around the world, the traces of these civilizations wait patiently for conscious minds to discover and interpret them. The stories they tell speak of achievements that dwarf human accomplishments in duration and scale, societies that managed global ecosystems for millions of years without written language or conscious reflection. The ancient protocols for cellular cooperation, refined across billions of years of evolutionary experimentation, continue their work in every living organism. The same molecular mechanisms that enabled the first bacterial communities to coordinate their metabolism still govern the cellular negotiations that maintain human bodies and minds. The deep time of biological civilization stretches backward into the darkness before consciousness, forward into futures that conscious minds can barely imagine. Somewhere in that vast temporal landscape, human societies represent a brief experiment in reflective awareness, the first time that biological complexity has become conscious of its own history and possibilities. The geological record preserves the stories of countless experiments in organization that preceded human awareness. Civilizations that built and communicated and governed themselves through biological technologies that operated without consciousness, but achieved remarkable sophistication nonetheless. Their traces remain in the chemical composition of the atmosphere, the architecture of ecosystems, the genetic heritage of every living organism. The planet continues its patient experiments with complexity, adding human consciousness to the long list of innovations that have emerged from the endless creativity of biological systems operating across geological time. The conversation begun by the first bacterial communities continues in new voices, new languages, new forms of organization that build upon foundations laid down in the ancient seas of deep time. Sleep comes gently to the civilizations of Earth, each in its turn settling into the quiet rhythms of geological rest. The stromatolites dream in limestone, the coral reefs pulse with tidal breathing, the forest networks whisper through fungal threads, the birds carry dinosaur songs into the darkness. Somewhere in this planetary symphony of organized complexity, human consciousness adds its voice to the ancient conversation, speaking words that the Earth has been preparing to hear for 4 billion years of patient biological innovation. The stories end where they began, in the quiet cooperation of cells that learned to work together in the earlier seas, establishing the protocols for complexity that continue in every heartbeat, every breath, every thought that emerges from the biological civilizations that came before and the conscious civilizations that may yet come. All part of the Earth's long experiment with organized wonder in the patient darkness of deep time. Word count 959.